AI Batch Inference: How Senior Engineers Optimize Throughput and Cut Costs in Production AI Systems. Welcome back to Agentic AI World. I'm your host, and this is episode 51 of our AI interview prep series. Today's topic, Batch Inference: How Senior Engineers Optimize Throughput and Cut Costs in Production AI Systems. If you've ever been asked in an interview, how would you process 1,000,000 documents overnight with an LLM? Or how do you reduce inference costs at scale? This episode is exactly what you need. Let's get into it. Section 1. What is batch inference and why does it matter? Batch inference is the process of processing multiple inputs together in a single model call, rather than one at a time. In online inference, you receive a request, immediately call the model, and return the result. Low latency is the priority. In batch inference, you collect a set of inputs, process them together, and the results are delivered later. Throughput is the priority, not speed. Why does this matter in production? First, cost. Most LLM providers charge the same per token whether you send one request or 1,000. But batch APIs, like Anthropic's or OpenAI's batch endpoint, offer significant discounts, sometimes 50% off. That's enormous at scale. Second, efficiency. GPUs are most efficient when they process data in parallel. A lone request uses a fraction of the GPU's capacity. Batching saturates the hardware and dramatically improves utilization. Third, reliability. Batch jobs are decoupled from real-time traffic. A spike in your online API won't crash your overnight analytics pipeline. Section 2. Core concepts every senior engineer must know. Let's cover the fundamental concepts. Concept 1. Request batching versus dynamic batching. Request batching is when you explicitly group inputs before sending them. You accumulate 100 documents, send them together, get 100 responses back. Dynamic batching is when the inference server, like NVIDIA Triton or TorchServe, automatically groups incoming requests that arrive within a short time window. The clients don't even know they're being batched. This is how high-performance serving systems reduce latency without sacrificing throughput. Concept 2. Batch size and memory trade-offs. Larger batches mean higher throughput, but also higher memory usage. If your batch is too large, you'll hit out-of-memory errors on the GPU. Senior engineers profile their models to find the maximum batch size that fits in GPU memory, then back off by 10 to 20% for safety margin. A useful formula: throughput scales roughly linearly with batch size up to the memory limit. After that, you start seeing diminishing returns or crashes. Concept 3. Padding and dynamic sequence lengths. LLMs require inputs to be the same length within a batch. Shorter inputs get padded with special tokens to match the longest one. This is wasteful. If you have one 2,000 token document and 99 10 token prompts, you're padding all 99 short ones to 2,000 tokens. That's enormous waste. The solution: sort inputs by length and batch similar length inputs together. This is called length-aware batching or bucket batching. It's a standard optimization in production systems. Concept 4. Throughput versus latency trade-offs. In real-time systems, you optimize for P99 latency, the 99th percentile response time. In batch systems, you optimize for total throughput. How many inputs per hour can you process? Senior engineers know when to switch modes. Real-time user queries need low latency. Nightly document processing, embedding generation, or classification tasks need high throughput. Using the wrong mode for the wrong job is a classic architecture mistake. Section 3. Architecture patterns for production batch inference. Now let's talk architecture. This is where interviews get interesting. Pattern 1. Queue-based batch processing. The most common pattern for large-scale batch inference is a message queue combined with worker pools. Here's the flow. Inputs arrive into a queue. Think Kafka, SQS, or RabbitMQ. Worker processes pull items from the queue, accumulate a batch of n items, or wait for a timeout. Whichever comes first, send the batch to the model, write results to a database or output queue, and acknowledge completion. This pattern is horizontally scalable, fault-tolerant, and easy to monitor. If a worker crashes, items stay in the queue and another worker picks them up. The key design decision is the batching window. How long do you wait to fill a batch? If you wait too long, you add unnecessary latency. If you don't wait long enough, batches are too small and GPU utilization suffers. A typical window is 50 to 200 milliseconds for soft real-time systems, or simply process when the batch is full for overnight jobs. Pattern 2. MapReduce style batch inference. For very large data sets, think millions of documents. You use a distributed batch processing framework like Apache Spark, Ray, or Dask. The map phase. Split your dataset into shards. Each shard is assigned to a worker that runs inference independently. The reduce phase. Aggregate results, apply post-processing, and write final output. Ray has native LLM integration with Ray Serve and is popular in production AI systems. Spark is better for teams already in the Hadoop/data engineering ecosystem. Pattern 3. Provider batch APIs. OpenAI, Anthropic, and Google all offer dedicated batch endpoints. You submit a SONL file of requests, and they process it asynchronously, typically within 24 hours, at a 50% cost discount. For use cases like document classification, summarization pipelines, or embedding generation, this is the cheapest option available. The trade-off is that you have no control over when exactly processing happens within that window. Senior engineers use provider batch APIs for non-urgent, high-volume workloads and reserve real-time APIs for user-facing features. Pattern 4. Streaming batch inference. Sometimes you need a hybrid. Process inputs as they arrive in micro-batches, without waiting for a full batch to accumulate. Apache Kafka streams, Flink, and AWS Kinesis support this. The inference worker processes micro-batches every few seconds, maintaining throughput while keeping latency acceptable. This is common for fraud detection, real-time content moderation, and recommendation systems. Section 4. Production challenges and how to handle them. Let's talk about the real problems you'll face in production, because interviewers love asking about edge cases. Challenge 1. Failed items in a batch. In a batch of 100 items, item 47 causes a model error. Do you fail the entire batch or just that item? Best practice. Process each item independently within the batch. Wrap each inference call in a try except. Log failures to a dead letter queue for retry or manual review. Return partial results for successful items. This is called partial batch success handling, and it's essential for production reliability. Challenge 2. Priority handling. In a batch queue, you might have two types of work: high-priority user-triggered jobs that should complete in minutes, and low-priority background jobs that can wait hours. Solution: use separate queues for different priority levels. High-priority queue gets dedicated worker capacity. Low-priority queue fills remaining capacity. When high-priority work arrives, it preempts or pauses low-priority workers. Challenge 3. Cost attribution and budget limits. At scale, batch inference costs can spiral. You need per-job cost tracking, budget limits, and alerting. Instrument your batch jobs to track number of tokens per job, estimated cost per run, cost trend over time. Set hard limits. If a job will exceed its budget, fail fast and alert. This prevents one poorly written query from burning your entire monthly AI budget overnight. Challenge 4. Model version consistency.